Okay, so there are several rules that apply to definite integrals, and just want to try to establish at least a visual understanding for as many of them as I can. I'm going to start with the first one, which has to do with the order of the interval, and this is one for which I'm not going to be able to establish any geometric intuition. You really just have to remember it. What the first rule says is that if I switch the order of the limits of integration, then it's like negating the integral. So, in other words, whatever value this integral has, if instead of integrating from a to b, I integrate from b to a, I just get the negative of that value. So just as an example, let's suppose that it's known that the integral from 1 to 7 of f of x dx is equal to 3. Then we can write that the integral from 7 to 1 of f of x dx is equal to negative 3. It's just a rule. There is an understanding of it, but it's a little deeper than I really want to get into, so I'm not gonna get into that. Okay, next rule is zero width integrals. So what happens if I integrate from a to a? If I integrate any function from a to a, it's sort of easy to see what happens there. In other words, what I'm doing is I'm taking this marvelous function y equals f of x, and I'm simply picking a point a, and I'm going to find the area under the curve just on this interval that has no width. So I have a region that has zero width. So that means that it's not going to have any area. I know that I've drawn this as having a little bit of width, but that's just because I don't have a pen of zero width. You have to think of this as being just an infinitely skinny line. So there's no area on an interval that has zero width. So you integrate any function from one number up to itself, then the interval is zero. So just for example, if I write the integral from 100 to 100 of sine x squared dx. We haven't even gotten into the question of how you would integrate a function like sine x squared, but that's the point. It doesn't matter what the function is. As soon as we say that I'm integrating it from a number to itself, I can simply declare that integral has a value of 0. Constant multiple, this hopefully has a little bit of geometric intuition, that if I take, let's say, this function, and right, so let's say that that's y equals f of x, and that the integral from a to b of f of x dx, let's suppose that this has an area of, let's say it has an area of 5. Well, if I double the function, in other words, if I instead write that function, so that's, hopefully I've drawn that to scale. So in other words, this is y equals 2f of x. I've just taken all the y values and doubled them. Then what I should get is I should get twice as much area. That's going to be an area of 10, because we know that if the area under f of x on the interval ab is 5, then if I simply make the function twice as tall, then I'm just doubling the amount of area. So that's what this rule means. So here we can say that in this case, this is the integral from a to b of f of x dx, and it equals 5. And what I've drawn here is the integral from a to b of 2f of x dx is equal to 2 times 5, or 10. That's how you would apply that rule. Okay, let's see. Sum and difference. Um, this sort of says what you'd think it would mean, that if I have two functions, suppose that I have let's suppose that I have this function, we'll call this y equals f of x, and we'll call this one y equals g of x. And let's say we have the interval going from 0 to 1 in each case. So if I were to add up these two little bits of area, so let's say that this is an area of 2 and this is an area of 4. If I decided to draw instead this function, oops, so this is going to be y equals f of x plus g of x, and I'll put that on the interval 0 to 1, then this should have the area of 6, because in other words, even though this curve, if it's not, I know it's a curve, we know line is a special case of a curve, this curve is simply the sum of this diagonal line plus this horizontal line. Um, if I add them up and form this sort of higher horizontal line, what I'm doing is I'm just adding the two areas together. That's what this means. So this is kind of useful because it means that that we can calculate if we have a function that's formed as the sum of two functions, we can just calculate their integral, but we can calculate their integrals separately. Oops, I forgot to put in the a and b here. It's going to be a and b there. Okay, so here what I'm drawing is this is integral from 0 to 1 of f of x dx. We said that equals 2. This is integral from 0 to 1 of g of x dx, and that equals 4. And here this is the integral from 0 to 1 of f of x plus g of x dx, and that equals 6. In other words, it equals 2 plus 4. So that's what this rule is saying. And by the way, it works for difference also. If instead of adding two functions, I subtracted them, it would work the way you think. We would simply take one and subtract the other from that. So you can look that up. You can look up the details of that. It's in the textbook. Additivity. This refers to the fact that we can break up the interval of integration. So let's suppose that I have the interval from a to b of f of x. So we know that if this is the area, in other words, this is the integral from a to b of f of x dx, gives us that area, I can pick any arbitrary point c in between a and b, and I can separately find the two integrals. Like, for example, let me just put in, I'll do this in pink and yellow. We can see is that let me write pink there and yellow there. So the yellow part is just going to be the integral from a to c of f of x dx, and the pink part is going to be the integral from c to b of f of x dx. It sort of makes sense that if I add these together, I'm going to get the striped region, which is the integral from a to b of f of x dx. In other words, you think about it, if I had, let's say, this rectangle, there's no reason that I have to calculate. I can calculate the area of this rectangle either all at once, or I can just divide it into two separate regions and add them up. It doesn't matter if I break it up somewhere in the middle. If I add them together, I'm going to get the area of the whole thing. And this is just a symbolic way of expressing that principle. Okay, the min-max property. What this says is that if, let's suppose, I have this function. I'll draw this a little bit carefully. There's a and there's b. So on the interval ab, there's a minimum value and a maximum value. So the actual area under this function is shown in red stripes like that. Let's suppose that instead I calculated the area of the rectangle whose width was AB and whose height was given by the maximum, by the highest point, the maximum of the function on that interval. In other words, I'd get this yellow rectangle. So what we know is that the striped area, this striped red area under the curve, has to be less than the area of the yellow rectangle. Why? Because the yellow rectangle is the area under the highest point that the function ever attains on the interval AB. The function itself attains that highest point, but it also attains a whole bunch of lower points. So it certainly makes sense that if what we're finding is the sum of the heights of all of the little skinny rectangles that you can draw under this function, they're going to add up to less than the area that we would get if we imagine that the entire function was this green line here. And we can do the same thing on the other side. We can say, imagine that the function is all just the minimum value. Let's calculate the area. Let me try this using a different color. If we calculated the area under the rectangle whose height was just the minimum value of the function, surely the function is going to have more area under it than the rectangle that's formed just by the height of its lowest point. So what this is saying is that the area under the curve, don't want to do that, that's the wrong pen. The area under the curve, which is given by this integral that I underlined in purple, is going to be is going to be more than the area of, this is the low rectangle, that's what I've drawn in blue, and this is the high rectangle. It's going to have to be somewhere in between these, and that's what this property says. Next property it's sort of related. It's called domination. I just want to be clear, we're not talking about anything that you might see in 50 Shades of Grey. This is actually just the technical term for this property. So what this is saying is that if I have this function y equals g of x, and I have this other function y equals f of x, then it certainly makes sense that the area under the blue function on any interval ab is going to be larger than the area under the purple function. Why? Because it's just it's just further away from the x-axis. So it's going to have there's going to have to be a greater area under f than there is under g. And then there's this special case where we say, well, what happens if one of the functions is just a constant zero, in other words, it's just the x-axis, then certainly there has to be more area under the blue function than there has to be more than zero area under the blue function if the blue function is greater is greater than zero. So that's what these properties are saying.